Today we're going to review the quotient property of square roots, and what it tells us if two quantities are being divided under one square root, so let's say 9 and 25 are being divided under one square root, we could simply break them up and take the square root of the denominator and the square root of the numerator individually and make sure that we still have division in between them. So this is the general terms of the quotient property. Make sure you know it well. This is just a reminder to us as we're going to use the quotient property with variables. Whenever we have an even exponent on a variable, that is a perfect square. So for instance, the square root of x to the 50th, since 50 is an even power, I should know what the square root is on its own without a calculator. And I'm asking myself what times itself twice would be x to the 50th, and that would be x to the 25th. As a review, if it has an odd exponent, like let's say x to the 51st power, we can't do that without breaking it down and rewriting that radical. So we'd have to split it into x to the first times x to the 50th, and then we would be able to evaluate one of those roots. But we know that the square root of a variable to the power of 1 is as simple as we'll get. So this is some background information when working with variables that we'll need today. So here's our first example problem that we can apply the quotient rule to. Let's say we're trying to simplify the square root of 20 over 16. The first method that we could use when we're working with the quotient rule is to simply rewrite the expression first. So in other words, if two numbers are being divided under one square root, we can split them and have the numerator take its own square root and the denominator get its own square root. So what we can do is just simplify them separately. So instead of the square root of 20, we could rewrite that as the square root of 4 times 5, which of course will be the square root of 4 times the square root of 5, which is just 2 times the square root of 5. On the bottom, the square root of 16 is 4. So I'm just going to carry that through. What we say down here is our final step. Make sure we simplify our answer. So in other words, if there's coefficients like 2 over 4, that would reduce to 1 over 2. So I should reduce the coefficients to 1 root 5 over 2. Or you don't need to include the 1. We could just leave that as root 5 over 2. Taking a moment to make sure that we understand we have simplified this and we haven't broken any of our simplification rules. There are no perfect squares left under the square root. In other words, there's no way I can rewrite 5 using one of our perfect squares here. There are no fractions under a radical sign, and there is no radical in the denominator of this fraction, so we know we are done. This does bring up a major idea for us though. So down here in blue, I just have our work from before. When we were trying to simplify the square root of 20 divided by 16, we broke it up into 2, and this is the answer we got just before. But one thing to keep in mind, it may be easier actually to simplify the fraction first. So for instance, instead of doing breaking it up right away, I could just simplify 20 over 16. 20 and 16 are both divisible by 4, so I could reduce that fraction first, which would be 5 over 4. Now, after I simplify that fraction, I need to continue to simplify the answer. And again, if I have one fraction under one square root, I could give the top its own square root and the bottom its own square root. Now, the square root of 5 will never simplify, and on this bottom, the square root of 4 is just 2. So we do get the same answer, and I would ask you maybe just to compare the work. Doesn't matter which way you approach these problems. You can either simplify the fraction first, or you can split the radicals and then simplify. Now, when we look at this example, we see we have two radicals in a fraction. So in other words, it's already been split up for us. So we actually don't need to do too much here in step number 1 because the top already has its own radical and the bottom already has its own radical. So we're going to just move on to simplifying each radical individually. So I'm going to copy the problem here. So we have on top the square root of 12 times a to the 4th. And on the bottom, we have the square root of 4 times a squared. Now here we can see the introduction of variables again, which we reviewed at the beginning and in other videos. So on top here, if there's two numbers being multiplied under one square root, I'm going to give the first number its own square root and the second number its own square root. And I'm going to do the same thing on the bottom. I'm going to give the number 4 its own square root and the number a squared its own square root. Now on top, I'm going to rewrite the square root of 12 as the square root of 4 times the square root of 3. And this is a perfect square because a to the 4th has an even exponent. So I know that a squared times itself would have given me a to the 4th power. On the bottom, 4 is a perfect square, so that's 2. And a squared is already a perfect square because of the even exponent. So what times itself would be a squared? That would just be a. A few more steps of simplification. I'm going to start to my work down here now. The square root of 4, well, that's just the number 2. I'm going to put a squared in front of the square root of 3. And then on the bottom, I have 2 times a. So I do need to reduce my coefficients, right? When I look here, I see a 2 on top and a 2 on the bottom. So those would be able to cancel away. And I see a's on top and a's on the bottom. There's one more a on top than there is on the bottom. So when I reduce this, there'll be one a left on top, and then we still have the square root of 3. So this would be our final answer. This does bring up another big idea. Like before, we said it might be easier to simplify the fraction before you do the radicals, and that's still the case. But what we're looking up here is you might need to combine the radicals back into one giant one first to help make the problem easier. So for instance, what I notice here is I have 2 separate square roots being divided. So that means I could combine them back together into one single square root. And the fraction, the numerator would have been 12a to the 4th, and the denominator would have been 4a squared. Again, I would ask you to pause the video and make sure that you could see how, when we rewrite this statement, it could really be written either way. So if we have one fraction under one square root, it might be easier to simplify the fraction first. So for instance, 12 over 4 could just reduce to 3. And then a to the 4th divided by a squared. There are more a's on top, so we'd be left with 3a squared. Now with this is just the product rule. If two things are being multiplied under one square root, I can give the number its own square root, and I can give the variable its own square root. Now, a squared has an even exponent, so that is a perfect square, which is a, and then the square root of 3 does not simplify, so we get a times root 3. Now what I want you to appreciate, what I'm going to do here is I'm going to put in a picture of our old work that we did on the last slide without simplifying the fraction first. So take a moment to compare the two work and think about which way you like doing it better. Notice how we do get the same answer as long as we follow all the rules. So the example that we have here, the square root of 14 over 16, is another important example because we've been talking about two different ways that we could approach this problem. So let's do option number 1, where we're just going to use the quotient rule first. So in other words, if I have one fraction under one square root, I could give the top its own square root, and I could give the bottom its own square root. Then I would simplify the top and the bottom separately. The square root of 14 has no perfect squares that go into it. 4 doesn't go into 14, 9 doesn't go into 14, and the ones after that, like 16 and 25, etc., are bigger than 14, so they obviously won't go into 14 evenly. So on top, we have root 14, and on the bottom, the square root of 16 is just 4. So our answer would be root 14 over 4. As we've been talking about, we could also simplify the fraction first and then deal with the radicals. So instead of splitting it up into root 14 over root 16, I could just simplify the radical first. So 14 over 16 would reduce to 7 over 8. Then from here, I could use the quotient rule and put the square root of 7 on top and the square root of 8 on the bottom. From there, I know the square root of 7 doesn't simplify because it doesn't have any perfect square factors. And on the bottom, I could rewrite the square root of 8 as the square root of 4 times the square root of 2. So finally, on top, I have the square root of 7, and then on the bottom, the square root of 4 is just the number 2, and then the square root of 2. Now, what we're looking at here is if we're trying to simplify, there can't be two different forms. So this is a good reminder to ourselves that we have to watch out to not break any rules. So I have the rules of simplification over here, and what I'd like us to see is rule number 3 of simplification says there's no radicals allowed in the denominator of a fraction. When I look here, I have a denominator with a radical. So this tells us for this problem, we wouldn't be able to use this method. That would be an incorrect answer. When that happens, we would either have to use the conjugate, which we haven't learned yet, or we're forced to use the other method. So just keep in mind that many problems can be done in two different ways, but some problems will lead you to an answer that's not actually simplified. So for this type of problem, we have to do it this way. This is the only simplified answer. So it doesn't matter which way you approach a problem, as long as your answer is always in the correct form. So we're going to do one final example to help summarize our work today and see all the different ways that we could do a problem. and again, summarize to make sure that we have all the main ideas. So on the left side, I'm going to use the quotient rule first. And then I'll go back and redo it and talk about the simplification method first, just so we can compare and start to develop habits and make sure we found a way that we like doing them best. So on the left side here, if we were using the quotient rule first, if I have two numbers divided under one square root, I can give the top its own square root, and I can give the bottom its own square root. Then from there, I just work on simplifying each radical separately. So for instance, on top, I can give root 48 its own square root, and I can give the a to the fifth its own square root, because again, if two numbers are multiplied under one square root, they can each have their own. Same thing on the bottom, if 12 and a squared were being multiplied together, they can each have their own square root. Now on top, 48 and a to the fifth are not perfect squares, so I need to rewrite them. So instead of 48, I'm going to rewrite that as root 16 times root 3. And then, as we talked about with variables, instead of a to the fifth, I can rewrite that as the square root of a to the fourth times the square root of a to the first. On the bottom, instead of 12, I need to get a perfect square factor, so I'll write that as the square root of 4 times the square root of 3. On the bottom, a squared is already a perfect square, so I'm just going to go ahead and rewrite that as a. So just copying my work down here, we need to do some simplification. So what we can do is the square root of 16, that's just a 4. The square root of 4 is just a 2. There's a root 3 on top and a root 3 on the bottom, so I'm going to cancel those. The square root of a to the fourth is a squared. Then we have the square root of a, because a variable to the first power under a radical will never be simplified. And then on the bottom, I do have an a. So finally, I need to do a little reducing. So 4 divided by 2 would just be 2 over 1. A squared divided by a, there's one more a on top, and then we still have the square root of a, which we could rewrite as just 2a times the square root of a. That's one way to do the problem. We should also see the other way that we had talked about. Maybe it's easier to simplify under the radical first and then use the quotient rule. So instead of breaking it up right away, I'm going to reduce the fraction 48a to the fifth over 12a squared. So 48 over 12, that just simplifies to 4. And when I start to simplify the a's, there's 3 more a's on top than there are on the bottom. So I would simplify to a to the third power. Now from here, after I simplify the inside first, I actually don't have a quotient at all. I'm going to use the product rule now, because I was able to eliminate the fraction by simplifying first. So if I have two numbers being multiplied under one radical sign, I can give the first number its own radical and the second number its own radical. Then from here, I can just simplify each of those. Well, the square root of 4, that's already a 2. And instead of a to the third, I would need to rewrite that as a squared times a. So then I get root a squared and root a. So I get 2. The square root of a squared is just a. And then I have the square root of a. So again, I'm going to get the same answer each time, and we just have to make sure that we understand there's many different ways we can approach these problems. Many of them will always lead us to the same answer as long as we're following the rules and making sure that we have done enough practice to understand which method we like best for which types of problems.